Welcome back to our series on electricity and magnetism. In this episode, we're going to talk about inductance, and we're going to apply the definition of inductance to one of the most significant inductors, the solenoid. Well, first, let's look at the definition of inductance. Inductance uses the letter capital L to describe the property, and the property is based on the number of coils that are influenced by the flux. NB or N phi is sort of the descriptor of the total impact of the flux on the inductance coil. And then we divide it by per unit of current. The units of inductance are the units of flux divided by the units of current. And of course, the units of flux are Tesla meters squared divided by amps. So Tesla meters squared per amp is the units, and that's known as the Henry. It's named after an American physicist who discovered inductance at about the same time as Michael Faraday. It uses the capital letter H. A Henry is a very large unit of inductance, so most inductors are in millihenries or microhenries. Well, let's apply the definition of inductance to find the inductance of one of the most important inductors we see, and that, of course, is an inductance coil or a solenoid. Of course, a solenoid features incoming wire, which then loops around and around and around some central non-conducting core. It's usually a cardboard tube. So the coil of wire wraps around and around and around, and of course current flowing through it from within causes a magnetic field to be generated, which collects straight down the core. We know the size of this magnetic field. The magnetic field of a solenoid is equal to mu naught times n. Little n is the coil density, the number of coils per unit length, finally times the current, I. That's actually flowing into the inductor. Well, let's use that together with our knowledge of the flux that the magnetic field would produce inside the inductor to actually calculate the L value for this inductance coil, for this solenoid. L then would be equal to N, the number of coils in the inductance coil, times the flux, which is the integral of B dot dA. And then all of that would be divided by the current. Well, the integral of B dot dA, at least for a solenoid, the magnetic field is constant right down the core of the solenoid. It's only a function of the current, but it's not a function of the cross-sectional area. So that integral in the numerator just becomes B times A. So it would be N, the number of coils, times mu naught times N, the density of coils, times I, times the cross-sectional area, and then all divided by I. So you can see what this produces is mu naught, and then I'm going to sort of fix the disconnect between the two ends. I'll change this n into the other style of n, so it becomes mu naught n squared. And in order to do that, I'll have to add an extra L to the denominator, A divided by L. And so there's the inductance. This is really the inductance per unit length, and commonly that's how they measure the inductance for an inductance coil, is the inductance per unit length, and it's mu naught times n squared times A. You'll notice that it isn't based on anything other than the physical properties of the solenoid. It's the square of the coil density times the cross-sectional area. So the bigger the solenoid gets, of course, the larger would be the inductance per unit length. What does inductance really mean, though? This is the inductance for a solenoid. There's the general inductance for any particular shape. Well, let's talk about it in the context of a wire loop we already know intimately well, and that is, of course, a simple circuit. If we had a simple circuit that consisted of a resistor, a switch, and a source of EMF, we know that as soon as the switch is closed, then virtually instantaneously a current I will travel around. This, in essence, is an almost practically steady state circuit, one that doesn't change over time. And yet let's re-examine that in light of this new variable, inductance. As soon as the switch is closed, of course, the current is going to go from nothing to its maximum value, and that represents a massive change in the flux through this loop. As a matter of fact, if the current goes this way, we can go ahead and use Ampere's law together with, or Faraday's law together with Lenz's law to say that there'll be a counter current and a counter EMF generated as a result of the inductance of this loop. That is, as a result of the current changing and increasing, it will cause the growth of a magnetic field in this loop, which will create a counter EMF that runs in opposition to the EMF driving the circuit. Now, of course, that EMF will be sensitive to the rate of change of current. And the rate of change of current will be dramatic at the beginning, but then it'll start to drop off, which means this EMF that's generated as a result of the inductance will be short-lived. Matter of fact, we can graph it. If we looked at the EMF that's generated by the inductance, it will start at the same value as the EMF for the battery. That is, initially when the switch is closed, current won't flow at all. But that will die out very rapidly so that within a few microseconds, the current will begin to pick up as a result of the EMF being generated by the inductance, reducing practically to zero. We can actually quantify that too. The EMF that's caused by inductance is equal to negative L, that being the coefficient, the value of the inductance, times the rate of change of current, di dt. Of course, as time goes on, the rate of change of current goes to zero, which is why the induced EMF drops down too. If we were to measure the current flow in the circuit, we'd see that it would match a very similar equation. Because the back EMF generated by the inductance will halt the current initially, the initial current, I, will be equal to zero, but it will grow rapidly to its maximum value. And of course, that maximum value will just be based on Ohm's law. This will be the EMF divided by the resistance. So the initial back EMF generated by the inductance will be equal to the EMF of the battery, but that will die rapidly. The initial current will be zero, but of course that will rise rapidly so that these both reach their steady states very quickly. One of the reasons why this circuit responds so quickly, and basically up to this point we've ignored the inductance that occurs in it, is that this construct is not a very good inductor. Because its inductance is very low, the value of the induced EMF will be correspondingly rapid. It will just be a tiny fraction of the rate of change of current. If instead we want the circuit to respond by raising its EMF very slowly over time, then we're going to need to do a better job building a construct that has a better inductance. And of course, the solenoid is perfect for that. If we took the solenoid and actually inserted it as a circuit element in the circuit, then it's going to do a better job at slowing down the rates of change of current. And that will be our next exploration, which is what happens when we stick an induction element in the circuit that's good at induction, as opposed to the loops that are naturally in circuits, which are bad at induction. That's going to form what's called the LR circuit. And that's the subject of our next episode.